Good morning, my dear students. Nice to meet you all. Good morning. Okay, very good morning to all of you. Right? Okay. Today I am going to start fifth unit, your last unit. Okay, design of footings. That is your last unit, fifth unit. That I am going to start today. Very good. Just a few minutes. Right. So I will project that towards. Okay. So today we are going to see design of footings, right? Pedestal and pile caps and all not that your syllabus. Only design of footings I am going to discuss with you, right? You know what is the function of a foundation? Actually, the function of a foundation, either you can call it as foundation or substructure. You know what is superstructure, what is substructure. Okay, the structure of a building below ground is called substructure, above ground is called superstructure. That and all you know. Okay, the function of a foundation or substructure is to safely transfer load from the superstructure to the ground. Okay, the function of substructure is to substructure or foundation is to safely transfer the loads from the superstructure to the ground. Okay, that and all you know. Different type of foundations, foundation structures are available. You know that, like isolated footings, continuous footings, like strip foundation for wall, no, continuous footing, combined footing, slab raft footing, okay, piles, okay, piles footing, pile groups, okay, and a piled raft footing, and then caissons foundation are used for this purpose. Like that, likewise, there are so many types of foundation you have studied already. Okay, design of foundation structure is a subject. It's in words. Okay, very good. Actually, here we are going to discuss about actually your IS code 456 class 34. Some provisions are there given for footings. Okay, design of footings. But you will not refer much this provision available in this 34. Okay, class 34. But most of the things you are going to theory involved. There is no expression formula available in IS code. The theory and all you have to understand, and you have to do in your own. Right? Very good. Design loads for a foundation. Okay, actually, a condition to be satisfied the subsoil in design of foundation is that its bearing capacity, which is based on both strength and settlement. No, so what is the soil can, the subsoil can withstand without excessive settlement. No, that is why it's based on both strength and settlement. Should not exceed by the load from the structure. Okay, as safe bearing capacity is operated from principles of soil mechanics. In soil mechanics, you have studied about what is safe bearing capacity of soil and all. For different types of soil, what must be the safe bearing capacity and all, you have studied already in your soil mechanics. By dividing the ultimate capacity of the soil by a suitable factor of safety. Okay, you know that we will take a ultimate bearing capacity of any soil. That will be suitable factor of safety will give you the safe bearing capacity of the soil. These values and all already you are aware of. Okay, please see here one important thing I want to tell you. Soil, okay, its value represents the serviceability condition. Actually, please see here, its value, which value? That dividing the ultimate capacity of soil by a suitable factor of safety, its value represents the serviceability condition actually. Okay, or not the limit state condition, right? The safe bearing capacity represents serviceability condition and not a limit state condition. Accordingly, the loads to be used to determine the size of the foundation should be the service loads and not the factor loads. Keep it in mind. In order to determine size of footing, you have to use only the service load. The characteristic loads you have to use. The service loads alone you have to use, because that load will be safe bearing capacity you are going to use. That safe bearing capacity is a serviceability condition. It's not a limit state condition. Okay, that is why in order to determine size of footing, you have to take into account only the service load. Okay, characteristic load, not the factor loads. Remember, and further design procedure you have to go for, because further design of that footing you will be doing by limit state approach. That is why there you have to take factor load. But in order to determine size of footing, because the load divided by bearing capacity you are going to divide, that bearing capacity represents the serviceability condition and not the limit state condition. That is why you have to take only the service loads. Accordingly, it's given. If dead load and imposed loads are considered, only one time dead load, one time drive load, service load. Okay, characteristic load. As it is, you are taking. You are not factoring. You are not multiplying with 1.5. You are multiplying with 1 only. No. Dead plus wind load, one dead load plus one wind load. If all the loads are considered, dead load, imposed load, wind load, one dead load, 0.8 live load, 0.8 wind load, they are model provision. Okay. You will not go to all three combination, only two combination only we will be dealing. So you will not think much about it, right? So keep it in mind, while determining size of footing, you have to consider only service load. Okay. Effect of horizontal loads. This and all effect of horizontal only for vertical load, vertically acting, actually downward, okay, direction acting load only we do it. Sorry, if the structure, the building frame is subject to lateral loads, horizontal loads due to pressure. What do foundation should be well anchored in the soil. Its anchorage and all will be taken care with the vertical face of the foundation. Okay, passive resistance of the soil in contact with the vertical face of the foundation will take care. Okay, not only that, see here, it will be noted that horizontal loads are to be resisted by friction and cohesion of the ground together with the passive resistance of the soil in contact with the vertical face of the condition. That will take care. Okay, you do not think much about this effect of horizontal loads. That if required, we can go for that. That and all will come in a design of pile foundation and all. Okay, for ordinary this one we will not write. So just I am reading out whatever available in your chapter textbook. Okay, basis of design footing. Basis of design of footings. Basis of design of footings. So area of footing. How do you determine service load on column? Whatever service load comes on column or wall above, that by bearing capacity of the soil below, right? That's what we take service load. Service load that alone remember, that is important here, not the factor load here, right? And then thickness of the footing and its reinforcement. The thickness should be sufficient to the main item to designed are. See, the main item which we are going to discuss here in this chapter are the thickness of the footings and its reinforcement. Okay, you are mainly going to determine what should be the thickness of the footing. Size of the footing you will be getting service load on from a column. Okay, in a column, bearing capacity of the soil will give you what will be the area of the footing. So, the size of the footing you can decide yourself, either square footing or rectangular footing. Once you know the area of the footing required, you can decide about the size of the footing and all, right? The next step is the important procedure is to determine what should be the depth, that to edge. What should be the edge depth of the footing? Sometimes the footing may be flat footing or sloped footing. That's why the edge thickness is important. Okay, what should be the edge thickness or say thickness of the footing? Okay, that we are considering the thickness should be sufficient to, very important. The thickness should be sufficient to. In what consideration we determine the thickness of footing now? It should resist the shear force without shear steel. Okay, the thickness of the footing should be in such a way that it has to resist shear. What type of shear it will be subjected, I will discuss later. Okay, in detail we are going to discuss. Okay, the shear point of view, but it has to resist shear. So, I will provide shear reinforcement. Some vertical stirrups I will provide. No, shear without shear reinforcement, the area of concrete available alone should resist shear. Okay, so the thickness should be such that it without any shear steel, it has to resist shear, and the bending moment without compression steel. Moreover, the bending moment, because you have this footing, the slab is loaded. No, sorry, the column load is transferred. So the projected part of the footing tends to bend. The projected part of the projected part of the from the column. There's a projected part of the footing. No, that footing tends to upward. Okay, to bend upward due to the soil pressure, upward soil pressure. Okay, the soil exert because the footing exert pressure on the soil. In turn, you get pressure from the upward pressure from the soil. Action and reaction. Reaction, no, reactive pressure from the soil. That's why they're going to be bending. Without any compression reinforcement. No, sir, the footing is subject to bending action. I will provide less thickness and I will provide some compression steel to take care. No, without compression reinforcement, only steel will be there in the only tension zone of the footing. In compression must be fully resisted by the area of concrete available. Okay, such a manner you have to put it thickness. But in many times, the shear point of view, the thickness is determined, not a bending moment point of view, less thickness required. But the shear resistance point of view, more thickness required. So that shear resistance most of the times determines the thickness of the footing. Now I am talking just theoretically. You may follow, you may not follow, but I am going to work out certain problem after the end. That time you will thoroughly understand. You will be understanding. Okay, no need to worry, right? This second point is not important. And then third point is withstand corrosion. Okay, that can be caused from the ground. Actually, the footing has to resist corrosion. It should withstand corrosion caused by the ground, isn't it? In ground, a lot of aggressive chemicals will be there. Okay. So the reinforcement available inside the column should not get corroded. Okay. For that, which one can protect the steel inside the footing? Obviously the cover of the footing. Okay, this minimum cover required is not less than 75 mm. Okay, when the concrete is cast against the ground, when you cast the foundation of concrete, okay, foundation concrete directly on the ground, the minimum the cover should not be less than 75 mm and not less than 40 mm when it is cast against a layer of building concrete. Okay, sorry, blinding concrete of 75 to 80 mm thickness. If some base concrete is put on that, the foundation is constructed, 75 to 80 mm is sufficient. However, the minimum cover required is not less than 75 mm. Minimum cover 6.4.2.2, where small provision in the IS code. It is available in page number 59. Okay, in 76, page number 76, these footings are there. Page number 59, you can see that provision. Okay, nominal cover to reinforcement, some general discussion is there. There, for footing, the minimum cover shall be 50 mm. For footings, the minimum cover shall be 50 mm. That provision is there. That's what mentioned here in this textbook. Okay. Right. So the thicknesses should be sufficient to take care of all these things. Okay. And then it is also important to remember that the percentage of steel provided. Okay. In the footing, the percentage of steel provided. Now the thickness point of view, we have discussed the points. Right. What should be the thickness of the slab? It has to resist shear without shear steel. It has to resist bending moment without compression steel. It has to clear cover, nominal cover should not be less than 50 mm or 75 mm based on the condition. Okay, whether the foundation is cast directly on the ground or there is a base concrete layer available, or in general it should not be. It should be around 50 mm. Okay, the cover should be not less than 50 mm. The cover. That's what. That way we have to decide the thickness of the footing. That's especially at the edge of the footing, because sometimes if you go for tapered foundation, the thickness at the edge is the thickness of the footing. Okay, that's what. And then now I am coming to the steel to be provided. So the percentage of steel provided should not be less than 0.15 for Fe4 250 and 0.12 for Fe450 steel, as specified for slab in IS 456 class 26.5.2.1. That's what. Already we have seen it in the design of slab. If you use Fe250 steel, the minimum reinforcement should be 0.15%. If you use Fe450 steel, the minimum percentage of steel used should be 0.12. Do you ask me to show that provision? Yeah, I can show you. Yes, I already noted 61, page number 61. Yeah, that's what the provision is there. Okay, where is that? Yeah, what is that? No. What is the class? It's mentioned, no. The class 26.5.2.1, 26.5.2.1, minimum reinforcement. That's what. The mild steel reinforcement in either direction in slabs shall not be less than 0.15% of the total cross-sectional area. Okay, total cross-sectional area. However, this value can be reduced to 0.12% when high-strength deformed bars or welded wire fabric are used. Okay, that's what. This already we have seen in this slab. Same thing is applicable to footing also. The minimum percentage of steel required. Okay, this is 0.12%. Remember, because we are using Fe415 grade steel. and then soil pressure on foundation. It is necessary that the center of gravity of the external load system always coincide with the CG of the total area, no doubt. So through the column, the load is transferred. No, the center of the external load system should coincide with center of gravity of the loaded area. Then only the pressure will be distributed uniformly. Okay. Otherwise, it will be non-uniform. Uh, but suppose the load is acting applied eccentrically on the foundation, the pressure distribution is non-uniform beneath, na, you can assume it as a linear. Okay. And also, otherwise, there will be a variation of pressure on the base of the foundation, which for rigid foundation, we assume the foundation is rigid. We are not taking into account the elastic deformation of the footing. Okay, we keep it, assume it as a rigid, may be assumed as linearly varying. The pressure is always assumed as linearly varying, either uniform distributed or if any eccentricity involved, because columns are not only purely subject to axial load. Columns are subject to axial load as well as moment, uniaxial moment, biaxial moment, and all you already seen the design of a short column. So, isn't it? So that is why there are going to be linear variation of pressure beneath the soil, right? Due to the moment acting on the column. So linear varying. In all layout of foundation, the basic principle should be always kept in mind. Okay, that's what. Next, conventional analysis of foundation subject to vertical loads and moments, right? So suppose how do you get that uniform pressure, uniform varying pressure beneath? Okay, it is given here with a vertical load P and a moment M acting on a column. The base pressure under the rigid footing will be non-uniform, but will be linearly varying from a maximum value of small q1 to minimum value of q2 as shown. Okay, and the line of application of P coincide, the value of q1 and q2 are given below. It's okay. What is see, you have a column. I will show you here. You have a column. Okay, the load is transferred to the footing column. The column is subject to axial force P as well as moment M, due to which okay, so the moment is acting like this. No, pressure will, here will be high, here it will be less. But we are assuming we are treating it as it's linearly varying. Okay, and this is the pressure is say Q1 here and Q2 here. You know how to get it. What is this one? P by A plus M by Z. Okay, here in the basics of your mechanics of solids you have studied. Okay, about column subject to moment. Here P by A minus M by Z. That's what I have written here. P by A plus M by Z. Here Q2 equal to P by A minus M by Z. What is Z? Z equal to, see this foundation in the plan. This is say L. The dimension perpendicular to this monitor. Okay, is say B, small capital B. Okay, size of the foundation. Width of the foundation B and length of the, width of the footing B and length of the footing L, say B into L. Okay. Now this, since we are considering this dimension, it tends to bend like this, no? So the Z is B L square by 6. That is the Z. Okay. The sectional modulus. So that's what. This is not a lot important. Again, you are going to apply your mind and going to do it. Just time being we are seeing. Okay. So Z equal to B L square by 6. Substitute in this. P divided by what is A? B into L. Width into length of the footing. Say electron footing, no? B is the width and L is the length of the footing. B L A is plus this M by Z, no? Z is nothing but this one. That's why if I put instead of Z BL square by 6, it becomes 6M by BL square. That's what. Q2 equal to P by BL area, no? P by area minus 6M by BL square. This way we can calculate wherever required. Okay. That's what. Some simple discussion we are doing, which you have done in your basics of mechanics of solids, right? And then what else to be? Yeah, produced by the resultant base reaction will be E equal to M by P. M by P will give you the eccentricity at the base. If required, you can compute it. Otherwise, no need. In your calculation, anywhere required, we can use it. Okay, that's what. And then what is this soil such as clays? Okay, these points are all not important. Our underlined not exceed 2 to 4, depend on whether it caused by the permanent attention or not necessary. Okay, see, I have skipped many pages of your textbook, which are not necessary. But in each chapter, the theory has been discussed in detail. Okay, you have a look at PC, Dr. Professor PC Varghese book. Whatever required for you, important for you, there alone I focused. Okay, that's what. Mm, so this analysis several pages I have skipped in your textbook, right? And then calculation of yeah, now I'm going to have a very important discussion with you. Calculation of shear for design. Okay, see, in many cases the thickness of the footing will be determined by the requirement for shear. That's what. Determining thickness of your footing. But the thickness of the footing will be determined shear only, the shear point of view. Because the shear point of view, you obtain thickness, no, that is always higher than bending moment point of view. You have to take a higher value. Okay, the thickness requirement in shear point of view, thickness requirement in bending moment point of view. When compared to bending moment point of view, shear point of view, the thickness requirement will be high. So obviously you have to take that thickness. Okay, that's what I mentioned here. In many cases, the thickness of the footing will be determined by requirements for shear. Okay, shear there are two types. One is one-way shear called wide beam shear. Another one is two-way shear called punching shear. Okay, requirements are prevalent as discussed. Okay, which are prevalent, which is going to be discussed now, right? See, a column footing will be subjected to one-way shear, that is wide beam shear, as well as punching shear called two-way shear. What is one-way shear and two-way shear? I will tell you before going into the statement here, right? See here, you have the footing, area footing, just a plan in plan is shown. Your column is here. Okay, your column is here. When the column transfer load to the footing, what will happen? The projected from the face of the column, whatever projected part of the footing is there, this tends to bend, uplift due to soil pressure, reactive pressure. The soil causes reactive pressure on the footing in the upward direction, upward pressure, due to which the footing tends to, because the column is acting, the footing tends to bend like this. No, the footing tends to bend like this, right? That's why this is the critical section for bending. See here, passing through the face of the column. This is the critical section for bending. This area, okay, this area is the critical area for bending. So if you want to determine the bending moment at this section, what to do? You have to compute the upward pressure, okay, the pressure caused. That pressure, upward pressure into this area, okay, will give you the total pressure, right? That into from here to the center distance. Okay, it is assumed to concentrate at center. No, that total pressure is assumed to the line of action of it is assumed to pass through the center. Into perpendicular distance means from here to that. Okay, that way you have to determine the critical moment at the critical section. Okay, and then we will do it. We will think actually this dimension into the depth of the footing, into the shear. Okay, the descent shear of concrete, descent shear stress of concrete, that is equal to, you have to equate to this force. From this you have to determine what should be the effective depth here. That I am telling orally, you may not understand, doesn't matter. We are going to see in detail while working out problem. That time you will understand, don't worry. Next, in the same beam, when it tends to bend, there is as there in beam, when a beam bends, there is a bending moment as well as shear force. No, as there in beam, here also the cross section of the footing subjected to shear force. Okay, but the critical section for shear force is not at the face of the wall, at a distance d, the effective depth distance. Effective depth to be determined, but that distance d, there you have the critical section for shear, that one-way shear. This is called wide beam shear. Okay, for that, this is the area called a critical section for one-way shear, shaded area. Critical section for one-way shear, shaded area is at a distance d from the face of the column. Only this area up to the edge of the footing. Okay, here from the face of the column to up to the edge of the footing, this area is critical section for bending. This area is critical section for one-way shear. That is called wide beam shear. It's just the area, see, it's look like a wide beam. No, that's why wide beam shear. Okay, this is one thing. For both you have to check this consideration. What is the effective depth required? You have to calculate. This one-way shear consideration, what is the effective depth required at this critical section? You have to determine. Okay, critical depth required na perpendicular to the monitor here. The depth required perpendicular to the monitor here. At here, the depth of the footing required perpendicular to the monitor here. The depth of the footing required perpendicular to the monitor here are to be determined. How to determine? I will discuss. Okay. Now I am discussing in terms of notation. It may slightly confuse you. While working with the numerical values, you will understand easily, right? Next, I am coming to two-way shear. Okay. When this is the footing, this is the column. When the column transfers the load to the footing, in addition, the footing tends to bend. When it tends to bend, there is a bending moment as well as a shear section, critical shear section at a distance d from the face of the column. Okay, we call it as one-way shear or wide beam shear. In addition to that, what happens when the column is acting a small area on the footing? No, due to which there is a punching shear. We call it as two-way shear. Sometimes the mode of failure will be punching. The column will go inside. If the sufficient thickness is not provided to the footing, it will fail by punching. I hope you will understand. Okay, punching, piercing inside. Okay, it will peer inside, no, punching, right? That is why the critical section for punching shear is at a distance d/2 from the face of the column. So all around the column at a distance d/2. Every depth to which every depth from the top of the footing to the center of the bottom reinforcement in footing. That is every depth there, perpendicular to the monitor here. Okay, remember d/2 at a d/2 na thickness, that every depth from the top of the footing to the tension steel at the bottom available, no, up to that, which is here perpendicular to the monitor here. Only the plan view you are seeing, it's not elevation, it's a plan view. Remember, elevation you visualize yourself, right? Just the side view of this footing, you visualize yourself, right? This is called a critical section for punching. Okay, so it is not shaded, it should be shaded actually fully it should be shaded, except this inside the dotted lines. Inside the dotted lines area, other areas should be just assume shaded. Okay, critical section for two-way shear. So the entire area is called a critical area for two-way shear, where d is equal to every depth. It also shown here. That's what. Okay. So one-way shear is similar to bending shear in slabs. That's what. One-way shear is similar to bending shear in slabs. Considering the footing as a wide beam, the shear is taken along the vertical plane, extending the full width of the beam. Full width of the base located at a distance equal to the effective depth of the footing. It's okay. That discussion alone is here. The distance equal to the half the effective depth of the footing. Okay. The allowable shear stress is the same as in beam. Okay. The allowable shear stress in concrete, that is tau c, suffix c, is the same as in the beam. In the beam you are using, no, you referred some table in IS code. Do you remember? Tau c, for tau c value, based on the percentage of steel provided and grade of concrete, you chosen some shear strength, okay, shear strength, design shear strength, tau c. Okay, in the design of beams, that is shear reinforcement design of beams. Okay, the same thing is applicable. The same tau c you have to use it here. In one-way shear, the shear force to be resisted is sum of the upward forces in the foundation area from the critical section to the edge of the footing. That's what. Tau V equal to V by BD. Okay, tau V equal to V by BD. Right. See, how do we do it? See here, this is the area, critical area, no? What we do, the upward pressure will be getting. That all working out a numerical problem, I will explain. You may not follow here. What the statement says, this total shear you have to determine. Okay, this upward pressure into this area will give you the total shear force to which the cross section is subjected. Okay, if you want the tau V value, nominal shear stress equal to this total force divided by this area will give you. Total force divided by the area of cross section here. The area of cross section at the critical section, that is L into D. Okay, will give you, right? That way you can determine here LD, you'll be getting LD, tau V equal to V by LD. Okay, and How do you get this one? What is the total shear force, resistance force here? The area here, L into D into tau C is equal to the total this one shear force here, which is this area, this plan area into the upward pressure will give you. From this, we are going to get what should be the D required here. Okay, that while doing a numerical problem, you will understand. That time again, once again, I will explain you. Okay, so that you will understand easily. With notation, if I explain, you may feel it hard. Since we are discussing, I am telling all these things. Next, I am coming to two-way or punching shear. Okay, which should be at a distance d by 2 from the column face. Already told you. Class 31.6.1 is taken as follows, right? Actually, this what do you call this punching shear value? Tau suffix p. Tau suffix p is punching shear, which is taken as 0.25 root of fck. Okay, let us see. That we will discuss later. Next, let S represents total upwards reaction. Let S represents the total upward reaction from the area between critical section for two-way shear and the edge of the footings. That is S. Let take S this one. It means what? Here, the area between the critical section, the dotted line is the critical section, and this is the edge. This is the edge of the footing. Okay, so the area between this, it should be shaded. I told you, no, this area into the upward pressure. Okay, will give you that is, take it as capital S. Okay, for punching shear, no, yeah, capital S. You take it as that is equal to here. What is the resistance should be offered by this section here, the dotted line, perpendicular to the monitor. Please listen here, perpendicular to the monitor, the area here. Okay, which is A plus B twice. Okay, A plus B into 2, because here one A is there, here one B is there. So A plus B plus A plus B. So 2 into A plus B. Okay, that into the depth here, that is D, into shear. Which shear you have to take? Punching shear, tau P. Tau P ki the values are available in ES code. Okay, this is here design shear, tau C. Here punching shear, tau C P, tau suffix P. Okay, that is equal to this S. You have to equate to this S. Okay, that's what written here. S equal to 2 into B plus A plus B into D into tau P. From this, we can calculate D. D equal to what you will be getting. Okay, so you have to, by considering one-way shear point of view, punching shear point of view, that is two-way shear point of view, and bending moment point of view, you have to determine the effective depth required for this footing. Finally, the highest value you have to take it as effective depth for footing. Okay, to determine the thickness of the footing is all such a computation you have to do it. In terms of notation, I am discussing with you. Some of you may follow, some of you may not. Don't worry. After completing this, we are going to see some worked example. No, there you definitely will be understanding clearly. It's easy only. Design of footing is very easy. Okay. So what else say the theory? Other minimum depth and steel requirement are already caudal provision, which already you are aware of. Okay, that's what. As already pointed out, the depth of footing are governed by the following consideration. That is, the depth should be safe in one way and two-way shear without shear reinforcements. That's what I told you. You have to see determine the effective depth required in that point of view. The depth should be safe and the bending moment without compression steel. Okay, the depth should be safe for bending moment without compression reinforcement. That also we are going to see there. Okay, and then the other third point is not important. The steel provided, that is about these points you should keep it in mind to determine the depth of footing. Okay, thickness of footing, and then the steel provided should not be less than 0.15% for Fe250 steel and 0.12% for Fe450 steel. That also we are going to check whether this reinforcement obtained is more than 0.12% or not. Okay, this is a minimum requirement as that of slab. Slab layer, the same requirement was there. Okay, that we are going to check. And then maximum spacing is 3D or 300 mm. The maximum spacing should not exceed 3 times the effective depth or 300 mm, whichever is lesser. Okay, effective depth of the footing you will be getting. The thickness of the footing you will be decide. You will decide, and okay, that is part of your design procedure. 3 times the FD depth or 300 mm, whichever is less. So the minimum spacing between the bars should be like that one. Sorry, maximum spacing between the bar. Maximum spacing between the bar. The spacing between the bar should not exceed 300 mm or 3D. Okay. The other discussion points are not necessary. Okay. I will skip. Anchorage length LD required. That also you can, while working out problem, you can see. Okay. Uh, right. Design of square footing of uniform depth. Okay. What is the time now? Oh, 12:31. Okay, I will do the one thing. I thought of even completing design of square footing of uniform depth today. The next class I thought of doing problem. Okay. Next class I will discuss this. Okay. So up to this I thought of discussing today. So that I can do problem next class. Okay, no problem. I will stop it here. Next class I will continue because we all will be in hungry. You know, so time already, right? Because online classes are supposed to be taken only for half an hour, not exceeding half an hour. It's okay. I will stop today's discussion today. Next class I will continue the continuity of this one, right? So I have recorded your names. Uh, I think still majority of the students are in implant training because continuously, I mean, there is no summer vacation, winter vacation for you because of the pandemic situation. You are attending implant training during this class hours. Okay, you have been permitted to attend. So majority of the students are implant training. They have to balance. Okay, so whenever they are free, they are attending online classes. Very good. Yeah, so I will be. However, I'm thankful to those who are attending class today. Right? Good. So with this, I will stop the recording first. If you want to discuss anything, you can discuss. Bye to all of you. Bye. Okay. So good.